All right, so hopefully nobody pops back on here because I'm doing your asynchronous because I'm in the zone. So we just did example 2, talking about this cylinder. We were looking at pumping liquid from a container. We were talking about rho times g, finding the area function, talking about the height as we measure it from the bottom of the tank, and kind of figuring out where those limits of integration are going to be based on how full the tank is. So we talked about this cylinder problem. We did the picture. We looked at like kind of making this layer of the water that was going to come out. And then we gave some like what ifs. So like if only this happened, or what if this happened or that happened, and then how that would affect things as far as your limits of integration are concerned, or this value H, depending on where we move that outlet pipe or outflow pipe. Okay, so I want to do 2 more examples so that you can kind of see how the area varies. I might go through these a little quickly because my husband's probably going to come in here soon and wonder where I am, but at least it's recorded so you can pause it and do whatever it is that you need to do while you watch it, which you can't do in class. I have to give you a little more catch-up time. Okay, so another example I wanted to do, I'll call it example 3. A tank is full of water. I'm going to draw you the tank because you're like, okay, a tank is full of water. Find the work required to pump the water out of the spout. Let me give you the picture of the situation that we're looking at here. Now, this looks, it's 3-dimensional, so I'm going to do the best job that I can possibly do here. It's going to look kind of like a trough. Kind of like that. And the ends look like triangles. That one is going to need to be redrawn. That one too. Do the best we can. Maybe I should have done the bottom first. Okay. I know sometimes these are hard to see if you actually put the back part of it in. Maybe I should remove the back part. Save myself some trouble. Okay. So this is your tank. It's 3 meters high. It is 8 meters long. And if you want, I can draw the back in like a, yeah, that's a little bit better. You're imagining, and maybe this will make it a little bit easier to see, there's water in this tank. I'm kind of drawing it below the top just so you can visualize this a little bit better. But this is what your tank looks like. So it sort of looks like a triangular trough, if you will. Now there's an outflow pipe that goes up 2 meters from the top. So we'll say this is 2 meters. So that is the situation that we're dealing with. Oh, I also need to tell you that this distance across the top is also 3 meters. Now, sometimes this is hard to see in 3 dimensions. It's almost like if you look away and look again, like once you see it, you can't unsee it kind of thing. But if you were actually looking at this from the front, so like let's imagine that you were standing right here, you were looking at this from the front, it would just look like a triangle to you. But your front view, if you would like to put it on a coordinate axis, would look like this. Where this would be 3 on the y-axis, because we know that the height is 3. And so I gave you that height being 3. That's what this represents right here. And then this width across the top is also 3, which means that this would be 1.5 or 3/2. And this would be negative 3/2, just so you get a good sense of what's actually going on with this tank. Okay, now we are going to pick a layer out of here. So remember how I said we're thinking about the area of the layer. And it's weird to think about a layer in terms of water because water is a fluid. But when you're thinking about a layer and we're moving this water up, we're pumping it upwards. When we pull this layer out, well, imagine that instead of just having this single line of water, this was my layer. And you could even fill it in if you'd like. So here's what my layer would look like from the sides. I don't know if I want to fill it in all the way. Might make my drawing look extra crazy, but this would be the outline of that layer. If you want to fill it in, it would kind of look like that. All right, so this is my layer. Now, I think that hopefully looking at this picture, you can kind of see what the area of the layer would be. Not exactly, but you can at least see the geometric shape. Now, I think most of us are thinking triangle because you're looking at a triangular shaped trough. However, notice that the layer is not actually in the shape of a triangle. Imagine that you're looking down on this shape. So you're above the trough and you're looking down. What you would actually see would be a rectangle. So your layer is rectangular. Okay, so that is key. Pencil issues. This is what I've been reduced to. Manual pencil. All right. All right, so we're looking at a rectangular layer. So however, note that as this layer moves up or down, it's not the same as it was with the cylinder. When we had the cylinder, we had this layer that was in the shape of a circle. And when we moved it up or down, it did not actually change the size or the area of that circle. Looking back at that picture, oh gosh, I've already lost it. Here it is. Your layer moves up and down and the area doesn't change because you're just looking at a cylinder with straight sides. You don't have a straight side situation here. But you know that when you're looking at a rectangle, all of the time, this width is going to be the same. When you move this layer up and down the tank is not going to change the actual width of your rectangle. The width is always going to be 8 all the time. What you need to know is what is the length of your rectangle. So what I'm looking for now is this piece. Now notice if the layer goes down, now all of a sudden this piece is going to shrink. It's going to get shorter. If my layer moves up, it's going to eventually get as large as 3 meters. or as small as 0 meters, kind of depending on where it is. So what I'm focusing on right now is this piece. So the length of the layer is this piece right there. The width of the layer is here. So I'm trying to figure out what the length is because the width is not changing, but the length is changing. So what you can do in this situation is notice that, well, you got two different ways to do this. One is a very mathematical way, and another is more of a visual way. I'm going to do the mathematical way because we're going to do this on one more example too. All right, so you're looking at your layer. If you're looking at it in 2D, it looks like this. So this piece also comes down here. Okay. Front of the drawing. All right, look at this function. You're looking at the rise over the run. We're going to actually list this as some function because remember what I'm looking for is a of y. All right, so the rise over the run is 3, and the run is 3/2. If I'm talking about this line right here, I'm going to write this as a function. So 3 divided by 3/2 is 3 times 2/3, which is 2. So y equals, oh, I don't want to say y, I want to see m. M equals rise over run. Sorry. I am going to use y in a second. So y equals mx plus b. In this case, b is 0. So y is just going to be mx, which is 2x. So this line is going to be y equals 2x. However, I need the area in terms of y. So I'm going to rewrite this as x equals, and then divide both sides by 2. And we'll write this as x equals 1/2 y. Now, what that means is that the value of x is always going to be 1/2 the value of y. I mean, you can easily see that here. The value of x is 1/2 of the value of y, which is 3. So the value of x is 3/2. And as you work your way down, that's going to be the same all the time. So you can sort of see now how that relates to the length of this piece. So I know that if I'm measuring this piece from the center, the length of it is always going to be 1/2 y. However, I need the entire length, looking at it compared to this drawing, the entire length of the layer is going to be twice 1/2 y, because I have not just the distance from the y-axis to the edge, but I'm also looking at the other half of that in the other direction. So the entire length of the layer is y. So we can think about it that way. I think that's going to be the best way to look at it in this particular situation. And you're going to see it again in one more example and to really solidify that. But now we can say that the length of the layer is y. And if that seems weird to you, you might need to go over this again and look at it again, make sense of it again, wrap your head around it again. Sometimes these problems you just kind of have to stare at for a while, and that's okay. I'm presenting it to you, I'm trying to do it in the way that I think is the most straightforward. And like I said, I'll use this concept again in another example so that hopefully you'll adjust to it. Okay, so we have now a function for the area of this rectangle. The rectangle is always going to be y units long, and it's going to be 8 units wide. So if y is sitting down here at 0, obviously the rectangle will have no area. But if it's y units wide, well, guess what? Up here at the top, it's going to be 3 units wide. Kind of see how that works when you plug in some test values. All right, so let's go ahead now and put our formula together, or our integral together for the work. So remember, I'm looking for the integral from a to b of rho g times a of y times h minus y dy. That's my formula. I'm moving water here. Did I say that? Yes, I did. Water out of the spout. So rho G, we talked about this in the last example, is going to be 9,800. Whoops. I'm going from A to B. In this case, the tank is full of water. If the tank is full of water, then I'm going all the way up from 0 to 3. So see how having this in two different views is going to be really helpful to you. So I've got a full tank. That means it's going all the way from 0 to 3. A of y, well, we already said that A of y is going to be, I guess I never technically filled the whole thing out. It's a rectangle, and it's the length times the width. So we'll say it's 8y for length times width. So we'll say this is 8y times h minus y. So h is the distance from the bottom of the tank that the water is being moved. Note that your outflow pipe is actually 2 meters above the top of the tank. So that means that it's 5 meters above the bottom of the tank, because you're going to take the 2 meters above the tank and then the 3 meters to get down to the bottom and add those together. So h in this case is going to be 5. You're going to have 5 minus y dy. All right, so there's your rho g, a of y, your area function for your layer, your rectangular layer. And then the distance that's being moved is 5 minus y, and you're going from 0 to 3. When you compute this integral, you will get approximately 1 million. Oh, I think this is an exact answer. 58,400 joules. Double check that on your own. You shouldn't need to double check it. It's done, but that's the answer that you should get. Now I'm going to do one more of these. Similar idea, a little bit of a different shape. Actually, I think this was the harder of the 3 examples that I'm showing you here for moving a liquid. So the last one I will show you, last example of 6.6, is example 4. A tank has the shape of an inverted circular cone I think you're going to see some of these on your homework, with height 10 meters and base radius 4 meters. It's filled with water to a height of 8 meters. Find the work required to empty the tank by pumping all of the water to the top of the tank. So here's the situation. You have an inverted circular cone. Hopefully we all know what that looks like. It's inverted, so it's upside down. So the situation, and I'm going to put this again on a coordinate grid because I think that's the easiest way to see it. Let's see. Your height is 10 meters. The base radius is 4 meters. So you're going up to the top at 10. And then the base radius is 4 meters. So let's see if that's 5. This is approximately 4. And you've got this cone. Looks kind of like that. It is filled with water to a height of 8 meters. So let's say 8 is right about there. That's where the water is filled to, 8 meters. the outflow pipe is at the top of the tank. So draw that however you'd like, but basically I just put like a hole there. So you can show like, okay, the water's coming out through that hole. Okay, now we're going to do the same type of thing we did with the last example. I want to figure out what is the area of a layer of water. So when I actually pick out a layer, any layer, pick a layer, any layer, put it right there. Notice that if I move this layer all the way down to the bottom, the area will go to nothing. And if you're wondering, well, what shape is this? It's not a rectangle in this case. We're looking at a cone here. So if you're looking for the area of the layer, you're actually looking for the area of a circle. So again, sit at the top of the y-axis and look down. If you sit up here and look down, what you're going to see inside that cone is a circle. So our layer right there is a circle, but the radius in this case of the circle is going to vary. So this is different from looking at the cylinder. When we were looking at a cylinder, the sides were straight, so the area of that circle was going to be the same all the time, no matter where you move the layer up or down. Not the case here. I move the layer all the way up to the top of where the water is, and I'm going to get a radius of 4. And if I move it all the way down to the bottom, I'm going to get a radius of 0. So that's the situation. So we need to figure out what is a general radius. So what is a general radius as a function of y? So I'm looking for a of y, our general radius of this circle. Now, our general radius is just going to be the distance from the center to the edge. And we're looking for an x value here, x equals. Well, we don't have that. So what we're going to do is we're going to use the slope to get a y equals, and then we'll rewrite it in terms of x. Same thing we did last time. So we're going to say the slope is equal to the rise over the run. Now, again, don't look here at what's happening at 8 because you don't know anything about the radius at 8. What you know is that at 10, the radius is 4. Let's make that really clear here. We don't know what the radius is at 8, so we can't say. But we can use the fact that if we go up 10 and right 4, we'll still be on this line for the side of the tank. So the rise over the run is 10 over 4, also known as 5/2. And then we have y equals mx plus b. B is going to be 0 in this case. So y equals 5/2 x. Multiply both sides by 2/5, and you'll get 2/5 y equals x. What that means is the distance from the center to the edge, which represents the radius of the circle, is always going to be 2/5 y. And we needed this as a function of y. So a of y is going to be 2/5 y for the radius. And remember, for a circle, we're talking about pi r squared. So we're going to go ahead and square this and multiply it by pi. Okay, so that's where this is going to come from. All right, so the radius of your circle is going to be x equals whatever 2/5 y is. And we're looking for that as a function of y. So if y is 8, well, that will give you your radius value at x. So if you're looking for the radius at 8, we'll just multiply it by 2/5 and get 16/5 as the radius down here, which is a little bit more than 3. 16/5, yes. Okay. So again, that makes sense. You can test out some values and make sure that this does indeed work for what you have going on in your figure. But like I said, this is going to be the hard part for you, finding the area function. Everything else at this point is just going to follow your formula. So we now can simplify A of y. We have it as 2/5 y quantity squared. Don't forget to also square the 2/5. So this is going to be 4/25 y squared times pi. And that's your A of y. Now you can start to put this formula together for the work to pump the water out of the tank. So we'll say that the work, and we're dealing with water here. Yes, filled with water. I said that in the problem statement. If you want to take the 9,800 and move it outside, that's fine. You know what? I'm going to put the rest of this inside the integral for now, and I'm going to simplify it in a second. I want you to see where everything comes from, matching it up with our formula. So we are going to go from A to B where the water actually exists in our tank. Remember, we said the water is filled to a height of 8 meters. So we're only going to integrate from 0 to 8 because that's where the water is. Once I have that, I already put the rho g here on the outside. That's where that goes. I'm just now looking for A of y, which is 4/25 pi y squared. And then the last thing I need is h minus y dy. And h in this case is going to be 10 because remember, we're talking about pumping water out of the top of the tank and we're 10 units away from the bottom of the tank. So h is going to be 10 and you'll have 10 minus y dy. Doesn't this look so easy when I do it? I know I get that a lot. Either way, I hope we can see now kind of where all these pieces fit in together. This, like I said, is going to be the hard part. You can pull the 4/25 out. 9,800 times 4/25 is 1568. Pull the pi out. That's what I would do if I were you. And then you'll integrate from 0 to 8 of 10y squared minus y cubed dy. Yep. And then what you should end up getting here as an exact answer is 1568 pi times 2048 thirds. Let's see, 1568 times 2048 thirds. This might have been one of those weird ones that my calculator just would not mess with. Yeah, it won't turn that into a fraction for me. So this is technically your exact answer, and that's measured in joules. The decimal approximation that you get for this, let's see, it's 3,362,827.797 joules, which you can reduce or simplify down to approximately, I mean, think about the number of decimal places you're being asked for, 3.4 times 10 to the 6. If you don't remember how to write scientific notation, if it's a +6, that means that your decimal has to move to the right to get to your original number. If it's a negative exponent, that's talking about smaller numbers. So bigger numbers are going to have positive exponents. But remember, you move the decimal point 1, 2, 3, 4, 5, 6, and it gets you right here behind the 3, which is where it shows up here. You could essentially write this as 0.34 times 10 to the 7th, but we don't do that. That's not standard notation here. So usually you just leave one digit in the front. So don't write this as 33.6 times 10 to the 5th. That's weird. One digit in the front, decimal place, and then think about what rounding instructions you were given, and then how many places did you have to move that decimal to get there. But that's scientific notation. These are approximate answers because a pi can only be approximate here. It's exact here because we have the pi included, which makes this an exact answer. So those were the other two examples I wanted to show you. So hopefully that helps you to get a better idea of how to find the area function. Like I said, you will be given some homework questions where you're going to be looking at area functions that are involving inverted cones. I think there are some hemispheres also. So a hemisphere is half of a circle. But the same idea. In that case, your radius is just going to be based off of whatever the equation is for that circle. I think that'll be even a little bit more straightforward than it would be for the cone, because for the cone, you have to come up with the function yourself, like we did here. If you were given a hemisphere, you're probably being given the equation. But if you are stuck, hopefully you'll bring your question to the student hour that I'm going to have at some point this weekend, or our regular student hour on Monday at 5 o'clock. From 5 to 6, I'll still be on Monday. Your test is Wednesday, September 15th. So I will send out an email this weekend as stated in class so that you have a really good idea of what you need to do to be ready for your test as far as your workstation setup and your camera angle and what you are and are not allowed to use, etc., etc. Email me if you have questions about any of this, and we'll help you. I will. All right. Have a wonderful weekend and enjoy working on these problems. I love these so much. I don't know what it is about them. I guess it's one of those things where it's so rewarding when you get the right answer, where it's just like, yes, I worked really hard for that. And I love the the figures are kind of fun to draw. Anyway, I could go on. Email me if you have questions.